So today we will discuss about some statistical basis of thermodynamics which are very relevant in deriving uh, Einstein solid or some specific heats of solid and regarding the paramagnetic and ferromagnetic samples as well. So as the course of statistical mechanics is not been discussed in due course in the same 5 of the syllabus, I will briefly touch upon few statistical mechanics classes for the upcoming few weeks. So to start with the statistical basis, we all know that a study of thermodynamics gives us the various macroscopic properties that are related through an equation of state, right? Having only two independent parameters. However, the equation of state cannot be deduced from the laws of thermodynamics. It has to be obtained experimentally. The ordinary laws of mechanics was the only tool to explain physical phenomena, and in certain cases, particularly where the system contains a large number of particles, ordinary laws of mechanics could not be used as it is impossible to follow the motion of each particle, right? So for example, a pinch of matter contains a very large number of atoms or molecules. I remember the order of the Avogadro number, that is 10 to the power 26 per kg mole, and therefore it is impossible to apply the ordinary laws of mechanics to a physical system containing large number of particles, particularly that of electrons. So such problems are, however, successfully solved by statistical mechanics. The larger is the number of particles in the physical system considered, the more nearly correct are the statistical predictions. Smaller the number of particles in a mechanical system, the statistical mechanics goes on becoming meaningless. So before the advent of quantum theory, scientists like Maxwell, Boltzmann, Gibbs, etc., so the scientists like Maxwell, Boltzmann, Gibbs, etc., applied the statistical mechanics methods, making the use of the classical physics. So these methods are known as the classical statistics or the Maxwell-Boltzmann statistics. The classical statistics successfully explain the phenomena like temperature, pressure, energy, etc., but fail to explain other observed phenomena like blackbody radiation, specific heat at low temperature, etc. For this, new approach was introduced by Bose, Einstein, Fermi, Dirac-like scientists. The Planck's quantum concept of discrete exchange of energy between systems are used. So the new statistics was subdivided into two categories. One is the Bose-Einstein statistics. Yeah. So, and another is Fermi-Dirac statistics. Thus, there are three statistics depending upon three different kinds of particles for which Maxwell-Boltzmann statistics. This is applicable to the identical and distinguishable particles of any spin, regardless of the spin, and the molecules of a gas are the particles of this type. The next is the Bose-Einstein statistics, and this is applicable to the identical but indistinguishable particles of zero or integral spins like 0 h cut, 1 h cut, 2 h cut, etc. So these particles are called bosons, and the examples of bosons are helium atoms at low temperature and the photons, etc. The next one is the Fermi-Dirac statistics, which is very much important in discussing various phenomena starting from free electron gas to the band theory of solids, where electrons are the most driving force and electronic spins are the origin of the magnetism in solids. So this is applicable to the identical and indistinguishable particles of half integral spins. That is, the spin is like half h cut, 3 by 2 h cut, 5 by 2 h cut, etc. So these particles obey Pauli exclusion principle and are called fermions. The examples of fermions are electrons, protons, neutrons, etc. So it is worth mentioning that the classical Boltzmann-Maxwell statistics is only the limiting case of the other two quantum statistics, namely B and FD statistics, and we will discuss later on about in more details of the both quantum statistics. Another important feature of the statistical mechanics is the principle of the equal a priori probability. That is, suppose we toss a coin, it is clear in mind that the coin will either fall with its head up or tail up. Similarly, if a six-faced cubical dice is thrown, it is sure that the dice will fall one of its six faces upward, as in the case of playing Ludo. In the same way, if we have an open box divided into two equal sized compartments, namely X and Y, and a small particle is thrown from a large distance, say from here, and then the probability of the particle to fall in the compartment marked by X is equal to the probability that it may fall into the compartment marked by Y. Again, there is an equal probability. So this principle of assuming equal probability for events which are equally likely to occur is known as the principle of equal a priori probability. So this is a very striking and most zeroth order law, I would say, in discussing statistical mechanics. A priori means something which exists in our mind prior to and independently of the observations we are going to make. So this principle of equal a priori probability will not hold good if in the above example the two compartments are of the unequal size. So the postulate of equal a priori probability is the fundamental basis of the statistical mechanics, and the basis for this postulate is provided by the ergodic hypothesis, ergodicity theorem, and according to the principle of conservation of density in phase space, the density of a group of phase points remains constant along their trajectories in a phase space. So if at any time the phase points are distributed uniformly in phase space, the phase points move in such a way that their density is uniform at all times, right? So the representative points move in the space in the same fashion as an incompressible fluid. For other spaces, the density will vary from region to region while there will be no change in phase space. This means there is no crowding together of phase points in any particular region of phase space. Okay. Then there is the concept of probability and frequency, which is very relevant in calculating the probability theory and permutation combinations as well. So directly I will discuss another important aspect and the most fundamental aspects, I would say, what is macrostate and microstate. So to start with macrostate, consider four distinguishable particles. I would discuss this simple example to clarify this macrostate concept from this basic understanding or the basic events of this, considering four distinguishable particles, and we wish to distribute them into two exactly similar compartments in an open box. So let the particles be A, B, C, and D. When any particle thrown into the box, it will fall into one of the two compartments, right? So since the compartments are alike, the particles have the same a priori probability of going into either of them and will be half. So the possible ways in which four particles can be distributed in two compartments are like in situation in like showed in the table. So this is compartment 1 and 2. So distribution should be either 0, 1, 2, 3, 4, and vice versa 0, 1, 2, 3, 4. So one possibility is 0, 4, another one is 1, 3, 2, 2, 3, 1, 4, 0. So thus there are five different distributions uh, and th these five distributions. Apart from these five, there would be no possibilities. So each compartment-wise distribution of a system of particles is known as a macrostate. So in general, for a system of n particles to be distributed in two similar compartments, the various macrostates are 0n, 1n minus 1, 2n minus 2, dot dot dot, and n minus 1, 1, and n0. So therefore, the total number of macrostate for n particles would be n plus 1. As for 4 particles, there would be 5 distributions. So therefore, for the macrostate for n particles would be n plus 1. And what is microstate? Since the particles are distinguishable, the number of different possible arrangements in each compartment is shown uh, in this fashion. If we distribute the possible arrangements of compartment 1 and 2 like this, and the last column of the table is the number of microstates, that is W, that is the thermodynamic probability. So for the arrangement of 0, 4 distribution, there would be no other composition rather than 0 ABCD. So 0 means compartment 1, 0, 4 means ABCD are in the same compartment. So there is only one possibility of arranging this 0, 4 distribution in compartment 1 and 2. For 1 and 3, what happened? If this compartment 1 is occupied by A, B, C, and D, then another possibility of filling compartment 2 is filling the other three particles apart from this one. So if this is occupied by A, then BCD is occupied by compartment 2. Likewise manner, for 1, 3 distribution, there would be 4 possibilities. For 2, 2, there would be 6. For 3, 1, there would be 4. And for 4, 0, there would be the vice versa of the 0, 4 distribution. So 1. So what would be the total number of microstates? This is 1 plus 4, that is 5, plus 6, that is 11, plus 5, that is 16. So each distinct arrangement is known as the microstate of the system, and the distribution 0, 4 can have only one arrangement. Distribution 1, 3 can have 4 distinct arrangements, and so on and so forth. Thus, a given macrostate may consist of a number of microstates. So in the above example of 4 particles, the total number of microstates are 16, that is 2 to the power 4. So in general, for a system of n particles, the total number of microstates are 2 to the power n. So suppose we consider a thermodynamic system of n, capital N, identical non-interacting particles occupying the volume V, and let E1, E2, E3 to EI be the energy of the particles of N1, N2, N3 to Ni respectively, then the total energy of the system would be E is equals to N1 E1 plus N2 E2 plus so on and so forth plus Ni EI. So the summation NiEi, and the total number of particles would be summation of Ni. So according to the quantum theory, the possible values of energy of each particle are discrete, and hence the total energy E also has a discrete value. But when the volume V is very large, the spacings of different energy levels are so small in comparison with the total energy of the system that the E may be regarded as almost continuous. The actual values of the parameters N, P, and E defines a particular macrostate of the given system. So there are a large number of different ways in which the individual EIs can be chosen so as to make total energy equal to capital E. So each of the different ways in which the total energy E of the system can be distributed among n particles constituting it specimens of microstate. Thus, a given macrostate corresponds to a many innumerable number of microstates, and it is very natural to assume that at any time the system is equally likely to be in any of the microstates, followed by the equal a priori probability. Right? So there would be another term called the thermodynamic probability, which is the number of microstates corresponding to any given macrostate is given its thermodynamic probability, and in other words, the thermodynamic probability of a particular macroscopic macrostate is defined as the number of microstates corresponding to that macrostate. So in general, it is a very large number and is represented by W generally, or the omega, and the bridge between the macrostate and microstate is the Boltzmann equation, that is entropy is equals to K ln omega. This omega is related to the microscopic state or the microstate of the system, and S is obviously the measurable quantity, the observable, that is the macrostate of the system. So this equation is called the bridge between microstate and macrostate, which is none other than called or derived by Boltzmann, and this is called the Boltzmann equation, where K is the Boltzmann constant. So quickly I will go to the discussion of some universal laws in statistical mechanics. Okay, so this is that. We'll first discuss the distribution of particles with a given total energy into a discrete set of energy states, as it becomes complicated when we deal with a very large number of n and possesses a quite complex energy pattern. A special procedure for handling such huge number of molecules has therefore be developed, and this is governed by some universal laws in statistical mechanics. Statistical mechanics is concerned with the properties of matter in equilibrium in the empirical sense used in the thermodynamics. So a little bit reminder of the degrees of freedom. So from the brush up of the degrees of freedom that we have already encountered in the course of the thermal physics, and from the statistical point of view, a monoatomic gas constitutes the simplest system, right? So this energy expression for a system involves small f coordinates of position and small f coordinates of momentum. So we then say that a system comprising one molecule has f degrees of freedom, and if there are of n molecules in the system, the energy expression for the system of n molecules has nf, n times f coordinates of position and nf coordinates of momentum. Thus the system has nf degrees of freedom, right? So little bit about the position space. Consider a system consisting of n particles distributed in a given volume V, and if the system is static, all particles will remain fixed at various points in space, and to completely specify the position of any particle in the three-dimensional space, we must know the values of its three Cartesian coordinates x, y, z, which are mutually perpendicular to each other. As there are n particles, a knowledge of 3n coordinates give complete information gives complete information about such a static system. So the three-dimensional space in which the location of a particle is completely given by the three position coordinates is known as the position space. And the small element in position space is denoted by volume element dv, and this expressed as dv is equals to dx dy dz. The momentum space, if a system is dynamic, its particles move about with various velocities and hence possess momenta. Complete specification of such a system cannot be described in terms of position coordinates only. For its dynamic system, we must specify the three components of momentum with the help of three velocity components Vx, Vy, Vz, in addition to the three position coordinates x, y, z. So if m is the mass of the particles moving with a velocity v, its momentum p is simple m times v, and the three components of momentum are px is equals to mvx, py is equals to mvy, and pz equals to mvz. Just as the position of particle is completely given in the three position coordinates x, y, z in three-dimensional position space, the momentum of the particle is completely specified by the three mutually perpendicular momentum axes px, py, pz in three-dimensional space known as the momentum space. And the small volume element in momentum space, that is dp vector or dqp, is nothing but dpx, dpy, dpz. Quickly move on to the phase space. The combination of position space and momentum space is known as the phase space, and thus the phase has 6 dimensions, right? Three position coordinates and three momentum coordinates, all mutually perpendicular to each other. The position of a particle in phase space is specified by a point with 6 coordinates x, y, z, followed by Px, Py, Pz. Complete information about any particle in a dynamic system can be obtained from a knowledge of these six coordinates, which completely determine its position as well as momentum. A small element in phase space is denoted by d tau and is given by d tau is equals to the product of dx dy dz, that is the volume element in position space, times the volume element in the momentum space dpx dpy dz dpz. A little bit about the mu space as the gamma space, as it is toward the mathematical concept. Let us limit ourselves to a system comprising of one molecule. Moreover, consider it to be a monoatomic as the simplest system. The state of the gas is completely known if the position and the momentum of each atom of the gas is specified. The position of an atom can be specified in terms of its rectangular coordinates xyz. This is known as the position space, and the momentum of an atom is completely known if its rectangular momentum components px, py, and pz are specified. So this is called the momentum space. These six coordinate quantities xyz followed by px, py, pz for each atom, when known, the state of the gas can be determined. The space covered by the infinite set of these six coordinates is called the phase space for a single monoatomic molecule. Since the energy of the molecule is given by px square plus py square plus pz square divided by twice m, which is equal to the p square by twice m, or the moment energy, the momentum space representation also gives the presentation of energy of the state. Such a six-dimensional space for a single particle is called molecular phase space, or the mu space, or the six-dimensional diagram cannot be drawn, and the phase space is purely, as I said, is the mathematical concept. Suppose that the position or momentum of one of the molecules is changed slightly. A phase point of this molecule will undergo a displacement in the phase space, and the microscopic state of the gas will be modified. To explain further, let us consider that the mu space or the mu phase space is divided into two-dimensional energy sheet having the position coordinates as x-axis and momentum coordinate as the px axis. So let us subdivide the range of variables x and px into arbitrary small discrete intervals called the phase cells of arbitrary size, as shown in this figure. The minimum size of phase cell is explained in terms of the classical statistics as well as the quantum statistics. What happened in the minimum size in classical statistics? The meaning of a point in phase space is well understood with the help of the Heisenberg uncertainty principle. If dx or the delta x be the size of the interval of the x-axis and dpx the corresponding length in the px axis, the phase space is divided into energy sheets of smaller and smaller energy ranges. The energy sheet thus consists of small cells of equal area, that is dx times dpx, which is nothing but h0. The state of the system can then be specified by locating a phase point within a particular cell of phase space. In classical description, h0 can be chosen arbitrarily as small as possible, and we may set it either 10 to the power minus 30 arc second or 10 to the power minus 35 arc second, or even smaller value. It may be noted that h0 or h0 has the dimensions of energy time. The lengths dx and dpx are assumed to be so small that if a phase point within a cell is slightly displaced to any point within the cell, the change in the position and the momentum will be so minute that even the most accurate experiment would be unable to detect the changes occurred. Such an infinitesimally small sized phase cell is considered. If the classical or if the particle lies within the cell, its state is represented by the pair of coordinates xpx. If there is a change in the state of the particle, it will move from this cell to another appropriate cell, and the dimensions of h0 is length time momentum, that is the meter into Newton second or Joule second. Excuse me. So what is the minimum size of the quantum statistics? As in the case of the Boltzmann time, there was no reason to ascribe any specific value of H0. All the results of classical statistics are independent of the size of H0, and therefore we permit H0 to go over to 0, H0 tending to 0, but the nature itself has provided a finite and constant volume for the unit phase cell with the discovery of the Planck's constant and the advent of quantum theory discussed under quantum statistics. We see that the assumption of dx dpx is equals to h is now consistent with the Heisenberg, so which is consistent with the Heisenberg uncertainty principle given by dx dpx minimum is equals to h, which is the value of 6.6 into 10 to the power minus 27 arc second or 10 to the power minus 34 joule second. According to this relation, dx dpx at the order of h, dy dpy is also at the order of h, dz dpz is h. Therefore, dx dpx, dy dpy and dz dpz is at the order of h cube. So this is the basics of the product of the volume element in the position space, and the momentum space is h cube, and therefore the volume of each state d tau is h cube. So therefore, according to uncertainty principle in phase space or mu space, the coordinates of a particle can be specified only to the extent that lying within the element of phase space of volume h cube, where h is the Planck's constant and the unit of the phase space volume is joule second whole cube. Another concept is the tau space, and if we are to deal with a system of n molecules, there are two alternative methods. One is to have the 6-dimensional 3 for position, 3 for momentum space representation, and we take n points to represent the positions and momenta of n molecules at a given constant instant. So this is called a mu space or the mu space representation. The another alternative method of tau space, tau or gamma space, sorry, this is gamma space representation, and it is a 6n dimensional phase space representation in which a single point represents a state of entire n particle system and is referred to as the representative point. This is in constant contrast to the mu space, which refers to only one particle, that is one point for one particle, and the gamma space representation is mathematically more difficult to handle. But it has one great advantage: if an ensemble, which is the assembly of all accessible microstate of the system corresponding to one macrostate, is to be represented, the 6n dimensional representation alone is applicable. So different points will then represent the corresponding all microstates of another macrostate, and the gamma space is considered to be a conceptual Euclidean space having two Fn rectangular axes. So for a general case of f degrees of freedom per molecule, we shall have position space which is f dimensional, the momentum space which is also f dimensional, mu space is 2f dimensional, and gamma space is 2fn dimensional. So if we divide or division of phase space into cells, then what happens? Let us consider a mu space representation. It is characterized by 2f dimensional phase space configuration. For a 2f dimensional phase space or mu space defined by position coordinates q1 to qf and momentum coordinate p1 to pf, an element of phase volume may be represented as d tau is equals to dq1 to dqf and dp1 to dpf, which is pi of 1 to f dqi dpi. So this is quantity that has the dimension length into momentum to the power f, or meter into Newton second to the power f, or joule second to the power f. Now suppose qi and pi are followed to take all possible continuously variable values. Then for a finite volume of phase space, there can be infinite number of representation points and hence infinite number of possible microstates. In statistics, however, we deal with finite number of microstates, howsoever large. Hence, phase space is divided into cells, and each cell of a certain fixed volume h0 to the power f. Therefore, in the element of volume of phase space given by the equation will contain the number of microstates that is d tau by h to the power f is equals to dq1 to dqf and dp1 to dpf divided by h0 to the power f. So here h0 is an arbitrary constant with a dimension of arc second or joule second, and this value of h0 is taken to be as small as possible, so the number of microstates obtained by this relation was large enough to handle with approximations. The gamma space representation having two Fn dimensional phase space, which is useful to describe a microstate of the system of n particles with a single point. An element of phase volume is given by dq1 to dqnf and dp1 to dpnf, and the number of phase cell in the volume element is given by d tau divided by h to the power nf is equals to dq1 to dqnf, dp1 to dpnf divided by h0 to the power nf. So if we discuss about the applications of these two, right, in the one-dimensional harmonic oscillator, so consider a linear simple harmonic oscillator of mass m and oscillating freely with frequency nu, and let us calculate the number of phase cells in the energy range from 0 to E. The phase diagram contains one position coordinate x and one momentum coordinate p, and so it is a px plane. At any instant, the total energy E of the oscillator will comprise of potential energy and kinetic energy. So the total energy E is equals to half kx square plus half mv square, and which eventually turns out to be 1 is equals to x square by 2e by k and plus p square by twice me. So if we cast this equation like x square by a square plus y square by b square is equals to 1, which is the shape of a ellipse, then the points of constant E lies on this ellipse, having the major and minor axis as root over 2e by k and root over twice me respectively. So for the energy range 0 to E, the phase area A is equals to pi AB. That is pi times uh, 2e by k times 2me to the power half, or 2 pi e m by k to the power half. So each phase cell has an inner area qi times pi is equals to h cut, and hence the number of phase cells in energy range from 0 to E will be phi is a function of E is nothing but pi by h naught 2e m by k to the power half. But the frequency nu is given by nu is equals to 1 upon 2 pi root over k by m, or phi e is equals to a e by h0 nu, or the energy will be E is equals to h0 nu times phi e, and thus if the oscillator is so governed that the number of phase cells can take only integral values, that is phi can take 0, 1, 2 to n, then we get n is equals to n h0 nu, and this means the energy can occur in discrete states and has values integral multiple of h0 nu only, which is the established case of the harmonic oscillator. Quickly we move on to the free particle system. For simplicity, consider phase space representing a single particle of mass m in a volume V, and let us calculate the number of phase cells in energy range from 0 to E. The volume of each phase cell is, say, H0 cube. An elemental volume in phase space is dpx, dpy, dpz, dqx, dqy, dqz is equals to nothing but dpx, dqz, dpy, dqy, and dpz, dpz. That is H0 whole cube. Assuming only 3 translational degrees of freedom, the phase space volume is V space is equals to integration of the whole quantity, whole integrand, or here the integration over all position coordinates q's gives the total volume, physical volume V, and the integration over all linear momenta p's is limited to px square plus py square plus bz square max is equals to twice me, that is p max whole square. So the phase space volume is V space is equals to V times 4/3 pi p max square, p max cube, 4/3 pi r cube. So 4 pi v divided by 3, 2a twice me to the power 3 by 2, and the number of phase cells will be phi e is equals to volume of the phase space divided by volume of one cell. That is v phase divided by h0 cube. So for a single particle, the number of accessible microstates will be equal to the number of accessible cells in the phase space, and therefore the number of microstates in the energy range from 0 to E will be given by phi is equals to 4 pi b divided by 380 cube twice me to the power 3 by 2. So for students, one example or one problem is for a single particle of mass m enclosed in volume V, show that the number of accessible microstates in the energy range E to E plus D rather than 0 to E is given by omega E is equals to 4 root 2 pi V divided by H cube m to the power 3 by 2 e to the power half delta E, where the phase space is divided by the rule del Qy del Pi is equals to H. So how do I calculate this problem? The number of microstates in the phase space having energies between E to E plus D is obtained by differentiating this equation of phi, as omega is nothing but del phi E del E, or the partial differentiation with respect to E. Thus we have 3 by 2 4 pi v divided by 3h cube twice me to the power half 2m delta E, which turns out to be this expression. And therefore we can say this sigma, this omega E is equals to 2 pi v by h cube 2m to the power 3 by 2 e to the power half d. These both two expressions holds good for the same problem. A little bit about the statistical ensemble. In statistical mechanics, Gibbs first introduced the concept of ensemble. It is obvious that a very large number, in fact infinite number of states of the gas corresponds to a given macrostate, macroscopic condition of the gas, because there are infinite number of ways to distribute the molecules in space. Through macroscopic measurements, we could not be able to distinguish between two gases existing in different states, two distinct representative points, but satisfying the same macroscopic conditions. Thus, when we speak of a gas under a certain macroscopic conditions, we are in fact referring not to a single state, but to an infinite number of states. In other words, we are referring not a single system, but to a collection of systems identical in composition and macroscopic conditions, but existing in different states. According to Gibbs, such a collection is known of systems is known as the ensemble, which is geometrically represented by a distribution of representative points in gamma space. Thus, an ensemble is defined as a collection of large number of macroscopically identical but essentially independent systems. This is very important term. And by the term macroscopically identical, we mean that each of the system constituting an ensemble satisfies the same macroscopic condition, that is volume, energy, pressure, temperature, total number of particles, etc. And by the term independent systems, we mean that the system constituting an ensemble are mutually non-interacting, just like the role of a non-interacting molecules in the kinetic theory of gases. So kinds of ensemble. According to Gibbs, there are three standard ensembles to which the real experiments could be approximated. These are, first one is the microcanonical ensemble, second one is the canonical ensemble, and third one is the grand canonical ensemble. This classification depends on the manner in which their systems interact. It has its own characteristic distribution. Physical systems can remain perfectly insulated from each other or can interact in a variety of ways. In particular, they may exchange energy or matter or both with each other. So a microcanonical ensemble is defined by is a collection of essentially independent systems having the same energy, volume, and number of particles. Same energy, volume, and number of particles. For simplicity, we assume that all the particles are identical. The individual systems of a microcanonical ensemble are separated by rigid, uh, impermeable, and well-insulated walls such that the values of E, V, and N for a particular system are not affected by the presence of other systems. So in the given macrostate, all the microstates having the same energy, volume, and the number of particles. So a brief introduction of the canonical ensemble. The canonical ensemble is a collection of essentially independent systems having the same temperature, volume V, and the number of identical particles N. Therefore, E can be exchanged. The canonical ensemble is defined by a particular system is in contact with a heat reservoir. Therefore, heat exchange can be possible. So, heat is a form of energy. So, exchange can be allowed in canonical ensemble. So this type of ensemble are characterized by three variables, namely temperature, volume, and the number of particles. So this is achieved by bringing all the systems in thermal contact with a large heat reservoir at constant temperature, or by simply bringing all the systems by the thermal contact with each other and represent symbolically a canonical ensemble. The individual systems of the canonical ensemble are separated by rigid, impermeable, but diathermic walls, that is conductive walls. As the separating walls are conducting, heat can be exchanged between the systems until they reach a common temperature T. Thus, in canonical ensemble, systems can exchange energy, but not the matter, that is particles. Grand canonical ensemble, there both kind of exchange can be possible, and here the systems are characterized by T, P, and mu. Mu is the new quantity called the chemical potential of the system. So in going from the microcanonical ensemble, in which the system in independent systems having the same energy and volume and number of particles, to canonical ensemble in which independent systems have the same temperature, volume, and the number of particles, the condition of constant energy has been relaxed, and this simplifies the calculation in thermodynamics where the exchange of energy can take place. And now the next logical step is to abandon the condition of same number of particles. Actually, in chemical process, this number n varies in various physical problems, that is radioactive decay. Thus, the grand canonical ensemble is a collection of large number of essentially independent systems having the same temperature T, volume V, and chemical potential mu. The individual systems of a grand canonical ensemble are separated by rigid, permeable, and conducting walls. Thus, an ensemble in which the systems exchange energy but not matter is called canonical ensemble. That in which both energy and matter are exchanged between the systems is called grand canonical ensemble, and that in which neither energy nor matter is exchanged is called a microcanonical ensemble. A specific choice of ensembles may be thought of as corresponding to a particular physical situation, and the microcanonical ensemble is fundamental and refers to the simple situation in which the constituent systems are isolated and not influenced by any of the external disturbances, and therefore it is the best suited isolated system. So this is the difference, major difference of the use of the ensembles, and we can use the partition function, which is again the most pertinent generating function of calculating various thermodynamic variables, of calculating pressure, energy, Helmholtz free energy, magnetization, this type of thermodynamic quantities. And the partition function Z is for microcanonical ensemble is delta of gamma. In case of canonical are integration e to the power minus beta e t gamma, and for grand canonical capital Z is equals to somewhere n equals to 0 to infinity to the power mu n divided by t times Zn. So this Zn is the same for the canonical ensembles like this. So there are many theories and expressions of derivations regarding this calculation of the canonical and canonical ensembles depending upon the physical situations where the exchange of the energy or exchange of the
matter, or both, for which kind of physical systems these laws can be utilized, and we can eventually give gives the B statistics and the FD statistics as well. So a little bit about the probabilities and the calculation of averages for the microscopic states in case of paramagnets, as we have discussed in the earlier classes. The role of the statistical mechanics is to create a bridge from the microscopic states to averages, and to this end, we want to know the probability for a certain microscopic state to appear along the system's trajectory in configuration space. Such a trajectory is described by giving the n tuples, that is sigma 1 to sigma n, in a certain time interval. This approach is replaced of necessity by the ensemble approach, in which the time evolution is ignored and probabilities are assigned to all allowed states. The ensemble is defined by the collection of probabilities or recurrence rates of every microscopic state, and we denote the probability of the state sigma 1 to sigma n by p sigma 1 to sigma n. Once p is given, the problem of evaluating averages becomes a mere technicality. So since if A is an observable, is a function of sigma 1 to sigma n and of a paramagnetic system in the microscopic state sigma 1 to sigma n, then the required averages is just A is equals to summation over sigma p sigma 1 to sigma n A sigma 1 to sigma n, where p is the probability, right? So where summation over sigma denotes the summation of all microscopic states. Thus the sum is over 2 to the power n states, wherein each spin takes on both possible values. In the case of spin j, each spin takes 2j plus 1 values, and the sum is over 2j plus 1 to the power 1 microscopic states of the system. Thus, for example, the average magnetic moment of the system in an ensemble defined by P is determined by the average of A is equals to M, that is mu B times summation upon sigma and summation upon sigma I P sigma 1 to sigma M, right? Uh, this one, mu B times summation upon sigma and again summation I upon sigma I P sigma 1 to sigma M. This value, you say, this value A is equals to M equals to this is nothing but the mathematical symbols can be reduced in writing this equation. In the simple cases for capital N equals to 3, we obtain average of M is equals to mu B times summation upon sigma 1 to sigma 3, sigma 1 plus sigma 2 plus sigma 3 times the probability P sigma 1 sigma 2 sigma 3, and where the summation is performed independently over sigma 1 sigma 2 and sigma 3, each assuming the value of plus minus 1. So there are a total of 8 possibilities, right? So next we show that how the average of M is proportional to the average magnetic moment of a single spin. So to this, and we define the probability for a given spin with I is equals to 3, for example, to have the moment sigma 1 either plus 1 or minus 1, and P sigma 1 is equals to, in prime system, this prime sigma summation prime denotes that we are summing over microscopic states with fixed sigma 1, or in other words we are assuming over all possible values of sigma 2 to sigma n, therefore p is a function of sigma 1 to sigma n. So of course all the moments are equivalent, so there is no special significance of sigma 1, and the prime can be attributed to any other spin I, and then the sum of this equation represents the probability P of sigma I for that spin to have the value plus 1 or minus 1. Thus, we can denote all of them by P sigma. So, eventually it turns out that the average value of magnetization is mu b n summation sigma is equals to plus minus 1 sigma P sigma, that is mu b n times sigma, where the average of sigma is the average of the observable A is equals to sigma I. So the transition, so if we discuss the paramagnet at a given temperature, that is this is the case of canonical ensemble. A system is kept at a fixed temperature when it is in thermal equilibrium with a much larger system referred to as the heat bath or heat reservoir. Clearly, the energy of the system under discussion is not constant, and since the system is in thermal contact with the heat bath, so that it can exchange energy with it. We thus have to determine the probabilities for states with different energies, and we propose that in such a case, the recurrence of systems in the ensemble describing the smaller system will be proportional to Boltzmann factor e to the power minus E upon kT, where E is the energy of the small system. The Boltzmannian proposal is not arbitrary. First, the kinetic theory hinted in this regard, and for the isolated paramagnetic system, the single spin satisfies the Boltzmann distribution in a state of equilibrium. So we pick from the isolated system a subsystem A of spins whose number n is very small compared to the total number of spins capital N, where small is far smaller than capital N, but still n is far greater than 1. For example, n is equals to 10 to the power 23 and small n is equals to 10 to the power 20, so that we may consider the rest of a heat bath. The probability for these spins to have value sigma 1 to sigma n will be the product of the probabilities for the single spins. Since as long as capital A small n is far greater than 1, there is no correlations, and we have learned that the constraint of a constant energy vanish when small n is very large. Hence, P is a function of sigma 1 to sigma n is equals to nothing but C times exponential of beta mu b h times summation upon I is equals to 1 to n sigma I, that is C times e to the power minus beta epsilon 1 to epsilon n. But the only constant is that E is the summation of epsilon I, where I runs index from 1 to n, and is the energy of the microscopic state with n spins and the microscopic state given by sigma 1 to sigma n. So we have to therefore the probability that in thermodynamic equilibrium our n spin system will be found in a specific state sigma 1 to sigma n and is indeed proportional to e to the power minus E upon kT, where E is the total energy of the state. And there may exist many states which have the same value of energy E and hence also the same probability. As we will see later on, we will have to take all of them into account. Then we can calculate the value of C inverse or 1 upon C as summation sigma 1 equals to plus minus 1 to sigma n equals to plus minus 1 to the power minus beta E sigma 1 to sigma n. And finally, this value, okay. The constant C in the equation is normalization constant, which ensures that summation, this one, summation P sigma 1 to sigma n is equals to 1, where the summation upon sigma denotes the summation over all possible configurations with sigma I is equals to plus minus 1 for each I, right? So that is, we require that summation upon sigma C to the power beta mu b h times summation sigma I equals to 1 to n sigma I is equals to 1 or C inverse is equals to summation upon sigma exponential beta mu b h summation I is equals to 1 to n sigma I, and the energy of a given configuration E is a function of E1 to a sigma 1 to sigma n, that is minus mu b times h summation I is equals to 1 to n sigma I. And the summation over sigma, in detail we can obtain that C inverse of this one is nothing but summation sigma 1 is equals to plus minus 1 dot 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 summation sigma n is equals to plus minus 1 to the power minus beta e sigma 1 to sigma n. So quickly go on to the partition function for the thermodynamic quantities. Uh, the calculation of the properties of the paramagnet whose temperature is 1 upon k beta is equals to T, or beta is equals to 1 upon kt, and we first define the important concept, that is the partition function, which is defined as summation over all microscopic states to the power minus beta e, or e is again over all microscopic states. The partition function z originates from the German name, that is Sum, which means the sum over states, right? So this function known as the probability theory is the generating function, is very useful in calculation of averages. And the idea is that we can replace the computation of the average of many observables of the computation of the derivatives of z with respect to the appropriate control variables. For instance, the average energy at temperature T is an ordinary average with probabilities P is equals to z inverse e to the power minus beta e, and the average e is equals to z inverse summation over sigma e sigma 1 to sigma n e to the power minus beta e sigma 1 to sigma n, where the summation is over all possible states of sigma 1 to sigma. And it reveals that the sum appearing in it can be written as minus del z del beta, and E is equals to minus 1 upon z del beta, or minus del beta of ln z. And in similar manner, it is possible to write the average magnetization in the form is 1 upon beta del ln z del h. So for the paramagnetic system, it is possible to directly evaluate this Z, since in the case each term in the sum is a product, making it possible to write Z. Therefore, Z is a function of beta A. This summation e to the power minus beta epsilon 1 is a function of sigma 1, epsilon 2 is a function of sigma 2, so on and so forth, as epsilon n is a function of sigma n. So now it is possible to sum over each of the variables sigma 1 to sigma n independently, and to write the sum of products as a product of sums, that is this way, individual term, right? So it is easy to see that every term in the product we appear in this equation is, one can write as small z is a function of beta h again, which is e to the power minus beta mu b h plus e to the power beta mu b h, and which turns out to be 2 cos hyperbolic beta mu bh, right? And hence capital Z beta h is equals to small z beta h to the power n. So it is possible to think of small z as the partition function of a single spin. So if we want to calculate from this, the average of E is equals to minus n del beta of ln small z, that turns out to be minus n mu b h tan hyperbolic beta mu b h. Obviously, the magnetization is obtained from this equation, like n mu b tan hyperbolic beta mu b h. So one can write this average energy is nothing but minus the field times the average magnetization, right? So the dependence upon this partition function, one can calculate the average value of energy, that is minus del beta of ln z, and the magnetization one, which is 1 by beta del then H of LZ, right? So a little bit about the nature of the susceptibility and the specific heat of the paramagnet. The behavior of the average energy and the magnetization as a function of external variable H and beta is determined by the behavior of sigma. In order to study it, it is convenient to define the dimensionless parameter x is equals to beta mu bh. And if we want to draw this sigma as a function of x as depicted in this equation, this figure, where sigma is plotted as a function of x, which is beta mu bh, this kind of behavior is obtained, and the graph may be interpreted in two ways, right? As the description of the average projection of the spin along the direction of the field as a function of h at a constant temperature, we see that at zero field, that is x equals to 0, here at the origin, there is no preferred direction and the average projection is 0. It starts to grow linearly with h, and finally, right, at a very large field, the average of the projection attains a full value of spin sigma is equals to plus 1. Namely, the polarization saturates here. The region x less than 0, this region, describes the case in which the direction of H is reversed, so that at saturation, the direction of the magnetization will also reverse and sigma takes the value of -1 here. As the description of the behavior of the average spin projection at a decreasing temperature, when the external field is held constant at very high temperatures, this x is equals to beta mu bh tending to 0. There is no difference between the probability for the spin to have a projection along the field and the probability for its projection opposite to the field. Hence, the average value of sigma tends to 0. When H is constant and T tending to 0, thermal energy finds it hard to flip spins, right? And again, the average spin projection tends to saturate the spin along the field. So more and more spins freeze along the direction of the field. Low and high temperatures are defined relative to the characteristic temperature capital theta, that is mu bh divided by k. And at very high temperatures, the energy of a single moment, that is mu bh, is negligible compared to the thermal energy kT. And very low temperatures, the reverse is true. Now, as mentioned, the low fields, the magnetization grows linearly with the field. This property is the main characteristic of the paramagnet. The coefficient of H is called the magnetic susceptibility, and it measures the size of the magnetic response of the system to changes in the external magnetic field. So if one can write the average of magnetization is nearly approximates to n times the susceptibility times the magnetic field, where chi is the magnetic susceptibility per spin. So its value is obtained from this equation with the help of the fact that tan hyperbolic x, right? This this value tan hyperbolic x is nearly equals to x for small x, and the result of chi, as a result, this chi turns out to be mu b square upon kt. And this existence of the inverse relationship between the susceptibility and the temperature was found experimentally by Puri in 1895 and has since then is referred to as the Puri Law. So we can learn from this equation the temperature decreases, the system magnetization also more easily, and the slope at the origin of this figure grows. This figure grows. As to the correspondence to the result with the experiment, we will return to the discussion as already discussed in the previous lectures. And finally, we can calculate the specific heat or degree of freedom at a constant field, since at a constant field delta Q, right? At constant field, what happens? At constant field, we all know that delta Q is equals to delta E, right? So clearly, CH is equals to 1 upon N times del E, del A, del T H constant. And this type of behavior can be obtained where x-axis is kt upon mu bt and this is ch upon k, right? So there is again possibilities of this high type behavior at a particular value, and there is a dependence upon the high temperature and low temperature limit again of uh, this kind of parameters. So at low temperature where Kt is far smaller than mu Bh, the temperature does not change the energy, and since each spin has the thermal energy of the order Kt but requires energy of order mu Bh to reverse its direction, so stated differently, the system is saturated and the energy is minimal. At high temperature where Kt is far greater than mu Bh, disorder is total and cannot be increased by raising the temperature. The Ch tending to 0 when T tending to 0 and when T tending to infinity, it also tends to 0, right? Ch tending to 0 when T tending to 0 and also 0 when T tending to infinity. Since there are in the problem only two characteristic energies, mu Bh and Kt, this is the thermal energy, this is the field energy. Clearly, everything has happens depends on the ratio Y is Kt upon mu Bh. Otherwise, changing the units would affect the behavior of the system. The two limits that we studied as y tending to 0 and y tending to infinity. So somewhere between them, we expect to attain this type of maximum behavior of Ch y is non-negative and must therefore grow near y equals to 0 and decrease towards y tending to infinity. The location of the maximum would be around y equals to 1 as both the thermal energy and the magnetic energy are significant in this region.